Alrighty, so we have this property for combining radical expressions, so products, we're multiplying here. What's really important to understand is you have to have the same index, right? So the nth right there, the nth root has to be the same in order for this to happen. So I take a look at example A. Can you simplify the product of the radical expression and explain? This is cube root, this is square root. Those are not the same indices, so not the same indexes, or however it's said. So no, you cannot. On B, they are. Both are cube root. So that means I can take what's underneath, the -4 and the 2 in this case, and I can multiply them times each other to get -8. So I want the cube root of -8 is a -2. So again, it's a pretty useful tool, as you'll see as we go through when I say to simplify things. Think of all those rules we've already listed for simplifying radicals. This one of those tools is going to get you there. Alrighty, so here, can you simplify the product of the radical expressions? This one, again, different indexes, so no, I cannot. This one's 4th root, this is 5th root, I cannot. Even though again, the number under the radical sign there is the same, I still cannot in this case. B, though, I certainly can. I can take the 5th root right here, and I can combine underneath, and I just multiply -5 times -2, and we can look for the 5th root of +10. And that is most certainly simplified right there. Alrighty, so simplifying a radical expression. So we can use that rule in reverse as well to pull things apart, which we've already practiced before. But again, using with cube roots. So what is the simplest form of the cube root of 54 x to the 5th? Well, we do know that 54 is... so again, 54 is technically 27 times 2. And luckily for us, 27 has a perfect cube root, so which is 3. And x to the 5th here, we can think of as x squared times x cubed. Again, I bring that up because that x cubed is the perfect square, or perfect cube, I'm sorry. So we can split them up. The reverse of multiplying them out, we can split them up. So I pull out the perfect cube parts, and I take their cube roots, so 3 and x. And the stuff that does not have a perfect cube stays underneath. Doesn't get changed. Do the same thing down here with your got it. So if you need to pause real quick to work the got it, please feel free to do so. Otherwise, I'm just going to continue. I'm going to write it. So the cube root of 128x to the 7th. You can think about that again as the cube root of 64 times 2, because 64 has a perfect cube. And x to the times x to the 6 and times x. Again, those two make up your x to the 7th. And I bring that up because, again, x to the 6th has a perfect cube. And if I were to rewrite this with the perfect cube ones in the front for the fun of it, so 4 is the cube root of 64, and x squared is the cube root of x to the 6th. Then the 2 and the x just come along for the ride. So I bring out those perfect cubes, and we get 4x squared times the cube root of 2x. That would be the simplified form here. Okay, a lot going on in this problem. I'm trying to talk slow and take you through it. Simplified form here. First thing I do is use that rule, right? You have to combine everything. Put them all underneath. Since they have the same index, they're both squared, or square root, I'm sorry. Now, once you put them all under there, then look for ones you can combine. So 720 times 10, or 72 times 10 is 720. X cubed times x is x to the 4th. Y squared times y cubed is y to the 5th. So now we've got them all together. So we have to start looking for our perfect squares inside of there. And 720 must be 144 times the 5. And obviously the x to the 4th is x squared, right? And y to the 5th is our y squared, and one more y along the way. Now again, noticing here, we've kind of in advance pulled out or sort of set aside what's going to be the perfect squares. So pull out those, separate them again, the perfect squares, and the leftovers, if you want to call them that. Now please remember here, the index was even, right? That means the absolute value thing, the absolute value signs are needed, since the index was even. Now, since we know that the index is even, but, again, you need the absolute value, but both of the things inside there are squared. There's no odd exponents. You don't actually need it again. You can throw it back away because the squaring takes care of any issues with negatives. So at the 12, x squared, y squared, and then the square root of 5y. Now again, please remember back to these absolute value symbols. If you were to forget and leave them on because of the even index, I would not count that against you, even though technically, again, you don't need them since everything. Now, if this were like, say, y cubed here, we would still need to keep them around the y cubed part. So, alrighty, there we have that one. Okay, to start off with this one again, notice they're separate, so we need to combine everything underneath. And what that looks like, if I just go ahead and multiply it straight out, at 1575 x to the 6th y to the 7th power. Now you may or may not know 1575, so 1575 is 225 times 7, and then again our x to the 6th, y to the 7th. I bring that up because 225 is our perfect square that's coming out of there. And we might even go so far as to say, well, technically y to the 7th is y to the 6th times y. So let's take a look at our perfect squares inside. 225 is really 15 squared. And x to the 6th is really x cubed squared. Same thing with the y. That's y cubed squared. And then the 7 and the y come along for the ride. So the perfect squares coming out are 15 x cubed, y cubed, and square root of 7y left inside. Now you might argue again that was an even index, so these are coming out as odd signs, so absolute value is needed for the x cubed and the y cubed. Not sure why the answer key doesn't have that. If we're going to stick to that, then let's do it that way, right? But again, that's one of those things where if you forget it, I'll be understanding, but I prefer you not because it is certainly part of the rules. All right, so continuing. Division, same thing. If you have two radicals, as long as the index is the same, you can go ahead and combine them under a single radical sign. So 18x5 over 2x cubed. Again, combined under the single radical sign. 18 divided by 2 is 9. And again, we learned our rules here quite a while back. X to the 5th divided by x cubed is x squared. We can pull out that perfect 3x. And one might argue putting an absolute value on that x is probably not a bad idea since this was an even index here. B, again, same thing, cube roots. So we can combine them underneath the radical sign. And then take a look here. Well, we know that 27 is a perfect cube, y cubed is a perfect cube, leaving just the cube root of 2 underneath once we separate them out, because 54 is 27 times 2. Pull out those perfect cubes, 3 and y, and leaving the cube root of 2 underneath. Again, simplified version here, making sure you get all the way down to the end of the rules that we did in the last couple sections. Okay, moving on with the got it here. So if we put both of those underneath the same radical sign, because they have the same index, we're allowed to do that. So 50x to the 6th over 2x to the 4th. We can reduce inside before we do anything. So here and here, leaving us with 25. Here and here, leaving us with x squared. So we end up with 25x squared. And again, when that comes out, we have 5, and then x. And again, we'll need the absolute value sign since this was an even index and it comes out as an odd power. Part B, can you simplify the expression problem 4a by first simplifying that? So each of those separately. And yeah, you can. I'll bring that up here to you as we take a look. There we go. Most certainly we can. So obviously we see we can cancel out leaving the two x's, right? So simplify each one separately. Let's say that first. That would allow us to cancel out the square root of 2x and 2x, obviously like so. And then that gets rid of this x and leaves just a single x up here. So same thing happens to work out in this one, but again, combining them sometimes lets you find perfect squares where they did not exist before. All right, so continuing. Now we've practiced this before. Same thing, going to continue with it. Rationalizing the denominator. So sometimes, remember we talked about that well-chosen 1, right? That helps us wipe out the denominator. No radical signs left in the denominator. So in this case, we start out here by clearing these up into their perfect squares. And we're going to multiply. So again, back up here, put them under the same, or split them up rather, I guess. Just like we can go ahead and combine them, we can also split them up. We have cube roots here. So that denominator, looking for the perfect cubes inside, we can go ahead and, again, rationalize the denominator by choosing that well-chosen 1. In other words, here it's the denominator over itself. This is the number 1. Don't forget that part. Go ahead and multiply it out. And the bottom, obviously, that wipes out any issues with a radical sign. And the top, that leaves us with 90x squared cube root of 90x squared y z squared. And as we look at that, we need to take a look. Do we have perfect cubes in there? Something we can pull out. So looking at this again, believe it or not, there are no perfect cubes left in the numerator. The denominator is completely rationalized, so we are done. Okay, so the trick here when we start is to start thinking about what you're going to do to pick that well-chosen 1 that you're going to multiply top and bottom by. And notice here, square root seems easier, right? It's multiplied by the exact same thing. This is a cube root, so I have to think about how am I going to create those perfect cubes. So to start out with, then again, we have the cube root of 7x over the cube root of 5y squared. So I had to think to myself, what is that well-chosen 1 going to look like? We're multiplying here. Well, I know that to create a perfect cube from y squared, I'd need another y, right? And to create a perfect cube from 5, well, I need to multiply by 25 to create 125. All right, so continuing. Sorry, I had to pause there, so I kind of forgot what I was saying. The kids were leaving, so. Alrighty. So anyway, I know that 5 times 25 creates 125, which is a perfect cube. So I'm going to say the cube root of, and I just was going to write 125, cube root of 25y. All right, so cube root of 25y. Again, this is that well-chosen 1. When it's squared, it's super easy. When it's cubed, you got to do a little thinking about it. So in the top, that creates the following. That creates the cube root of 1/7. Oh, for Pete's sake. There we go. Thinking of where it's going to land here. Cube root of 175 x y. Okay. So again, it multiplies straight across, right? Same index, so I'm allowed to do that. In the bottom, that creates the cube root of 125 y cubed. Now again, notice our index here in the bottom is, on top, is odd, so I don't have to worry about that whole absolute value thing. So we have on the top, believe it or not, there are no perfect cubes in that. 175 xy, and in the denominator, cube root of 125 is 5, cube root of y cubed is y, and that's it. So again, that well-chosen 1 is our trick here. That's our thing. We got to have that. So part B, which choice in problem 5 could be eliminated immediately? Explain your reasoning. Well, D, because if you go back to it, there's no y in the expression, so like, oh, that's out. So a little bit of thinking ahead kind of thing there. But again, the moral of this story right here is that well-chosen 1.